Hi everyone. Today let's talk about section 2.3, techniques of computing limits. Big idea. The limits of many familiar functions as x approaches a value of a is simply the function evaluates at a. So i.e. the limit equals to the function evaluate at a. So this is for a lot of functions, but it's not for many functions, but not for all the functions, okay? We will talk about that in session 2.6. This is only true when the function is continuous. Big skills. You should be able to compute exactly the limits of many familiar functions using the theorem from this session. So first of all, let's look at limits of linear functions. Let a and b and m be real numbers. For linear functions set f of x equals to mx plus b, then the limit of f of x is just we plug in a for x. Okay, so why is that? What is the linear function looks like? If the slope is positive, we have this. Slope is negative, like this. This is when slope is 0, and this is when the slope is undefined. And you can see when we draw the line, we draw it without lifting our pencil from the paper. So it's actually continuous. So if the function is continuous, we'll talk about what it means by continuous. But one of the big property is the limits of f of x when x approaches a equals to f of a. And here we have the limit laws. Assume f and g has the limits, okay? The following properties hold, where c is a real number and m is greater than 0, n is greater than 0, they are integers. We have the first sum law. The limits of the sum equals to the sum of the limits. The difference of sum equals so the limit of the difference equals the difference of limits. And constant multiple, we can pull out the constant c, okay, outside of the limit. And limits of product equals product of limits. Limits of quotients equals quotient of limits, provided now the denominator cannot be 0. So if the denominator is 0, we cannot separate them in the numerator and denominator. Okay, for example, if you have like x goes to 0, x squared over x, something like this, that is not equal to x squared over x, because this guy is 0. You cannot have 0 in the denominator, right? So what it is actually we can simplify it, right? Because x is approaching 0 and x is not exactly 0, so we can cancel the x and then we get limits of x. Well, that is 0. So this is how we solve it. Okay, so don't separate as the numerator and the denominator. Okay. And next, we have the power law. The limits of a power, we can actually move the limits inside of the power. Okay, for fractional power, we have to be very careful because we also need to require f of x to be greater or equal to 0. Okay, and because sometimes think about it, if m is 2, then 1/2 is like square root, while you require the things inside the square root to be greater or equal to 0. Okay. And so here are the limit laws and the limits of polynomial and rational functions. Assume p and q are polynomials and a is a constant. Then for polynomials, the limits p of x equals to p of a. Because polynomial, when we draw it, you can see is continuous. So that's why when we evaluate the limits, we can just plug in the numbers into the function. And similar with rational functions, but you have to be careful. The denominator cannot be 0. Okay, so if the denominator is 0, Either you have 0 over 0, that means there is a bad guy, you can factor out that bad guy and cancel it. Or if you have constant over 0, that means you're gonna expect to have positive infinity or negative infinity. So let me write it down. So 0 over 0, it means there is a bad guy. We can factor it and cancel it. And if we have constant over 0, because we're not exactly 0, it's actually a number getting close to 0, so this will give us plus or minus infinity. And it depends on how many minus in the factorization, okay? We mark. These limit laws also holds for one-sided limits. So we can replace the two-sided limits by the left-sided limits or the right-sided limits. Alright, so after we talk about the laws, let's do some example. So example 1. Limits x goes to -1, 3x squared minus 4x plus 1 over 2 minus 5x. So part A, find the limits using limit laws and specify which law is used in each step. Okay, so part A, we copy down. So we look at the format from the outside to the inside. Well, the outside format is a quotient, right? So we use quotient law. So we move the limits inside the numerator and denominator. Alright, and what is the quotient law? Quotient law is law number 5, right? Okay, so this is law number 5, the quotient law. So next, we're gonna want to distribute our limits. Well, this is the sum law and difference law. So law 1 and 2, okay. So then now we have limits 3x squared minus limits 4x plus limit of 1 is 1, and then we have limit 2 minus limit 5x. Okay, we can do one more step. We have the 1 here. Okay, so next we continue. Okay, so for constant multiple, we can move the constant outside of it. So this is law number 3, constant multiple. Then we have 3 limits x goes to -1, x squared minus 4 limits x. Limit of 1 is 1 because it's a constant function. And limit of 2 is 2. And then we have 5 limits x. Alright. And then you can see, well, x squared, we can move the limits inside the square. Okay. And then here we're using the power law, that's law number 6, right? And then we have limit, well, forget the 4, 2 minus 5 limits, x goes to -1x. Okay, finally, we know the limits of linear function, okay? So we know the limit for a linear function is simply we just plug it in. So then we have 3 minus 1 squared minus 4 minus 1 plus 1, 2 minus 5 times -1. That is 3 plus 4 plus 1 over 2 plus 5. Well, that is 8 over 7. Okay, so that is part A. How about part B? Okay, so part B, use the limit of rational functions. Well, rational functions says that we can just plug in if the denominator is not 0. So part B goes from here directly to this step. So it's just like we don't need to write out the details for the laws, okay? It directly goes from there to we plug in the numbers if the denominator is not 0, okay? Yeah, so that is part B. Okay, and actually this is how we prove the limit law for a rational function. Well, you first move to the numerators and denominators, and you use the sum law, difference law to split the terms, and then if you have powers, you just move the limits inside the powers, and then finally we know for linear function we can plug in the numbers. So that's why this is actually the kind of similar proof to how to prove the limit law for rational functions. Okay, so let's continue. So example 2, suppose, so here we don't know the expression of f, g, and h. We only know the limit when x goes to 2. So what do is we're gonna follow the limit laws. Alright, so let's do it. So first of all, we can see this is a quotient, right? So let's move the limits inside the numerator and the denominator. And this is limits. So don't forget, you gotta include the limits in each step. Okay, so don't be lazy. You can't be lazy. Include the limit in each steps. So next we can move the limit inside. So we get 4 roots. And then we have limits. X goes to 2. So we can actually split as well, right? And g of x, we can move it inside the power as well. 5 limits. H of x minus 1. Oh, almost ran out of space. And then here we can split g of x and the limit. Oops. No negative here. Oop. And h of x plus 3. We can factor out the 3. We can move out the 3. And then cosine x minus 2. Okay, so far so good, everybody. Now we're ready to plug in, and this is 4 roots of, so limit f of x when x goes to 2, that is 7. And then g, we have 4 squared plus 5 times negative 6 minus 1. The bottom we have 4 and negative 6 plus 3. Cosine, when we plug it in 2, cosine 0. Cosine 0 is actually 1. Okay, so this is cosine 0 is 1. What's cosine looks like? Like that. Okay, so the graph of sine and cosine are very important. You need to remember it. And then 4 squared is 16. 7 times 16. 7 times 6 is 42. 7 times 1 is 7. So 1, 2. Minus 30 minus 1. Negative 24 plus 3. Alright, let's continue. What's the numerator? Well, that is 82 minus 1, 81. So 4 roots of 81, and then we have minus 21. What's 4 roots of 81? 3, right? 3 to the 4th is 81. Oh, we can actually cancel. We have a common factor 3, then we have 7 in the denominator now. Okay, so this is the complete proof for this problem. Let's continue. Okay, so here we're gonna have more exercise about the limits. Do you remember the steps of how to compute the limits? So let me remind you, okay, the first step we want to plug in the number. Okay, if you get a number, that is good. But if you get 0 over 0, what does that mean? There is a bad guy. Okay, so we need to go to step 2. Step 2, when we see rational functions, when we see polynomial in the numerator and denominator, we want to factor it. And then you can see the bad guy and you can cancel the bad guy. Last time we also talked about when we see difference of square roots, we multiply by the conjugate. Right? What's the conjugate? Well, that is the sum of the square roots, right? And then we have one more case we will see today. And then the last step, after we cancel the bad guy with safe, we can plug in the number again to evaluate the limits. Alright, so let's see here. Okay, so this is the problem, and we see their polynomial, so we want to factor it. Are you good at factoring? Okay, how do we factor it? X, how do we get -7? So we have -2 and -5, right? And then we get -2x and -5x. That will give us -7x. But how about the denominator? Well, the denominator, we actually need some formula. I hope that you're familiar with all the algebra formula. Okay, so the common one we will use a lot is, well, this guy we use a lot, especially when we see difference of square roots, right? We use it to get rid of the square roots. And then this guy, we know that, right? A lot of people forgot about the 2ab. Don't forget the 2ab, okay? It's so important. And when you have minus, you have minus here. Okay, and then next, we're gonna have a cubed minus b cubed. How do we factor it? This is actually equals a minus b, and then a squared. So if this guy is minus, then this guy is minus, then this guy is, you flip the sign, become positive. And then you have ab. So not 2ab, just ab plus b squared. Okay, if this guy is plus, what do you do? Well, this guy become plus and this guy become minus. Okay, so for this algebra formula, I hope that you can memorize it. For Calculus 1 and Calculus 2, there's no formula sheets are allowed, okay, in the exams. So all this formula, I hope that you are familiar with them. Okay, so let's continue. How do we factor it? Well, 8 is like 2 cubed, right? 2 cubed minus x cubed. Then we use this formula. And then with a is 2, b is x. So that equals 2 minus x. 2 squared is 4 plus ab is 2 times x. b squared x squared. Okay? Some of you say, oh, they're the same, we can cancel it. No, they're not exactly the same. But how do we make them the same? How can we flip them? So when we flip them, we actually gain a minus sign. Why is that? Well, you can think about, well, when you distribute the minus sign, it becomes minus x minus -2. So this is minus x plus 2. That's exactly what we had before, right? So that's why when you want to flip them, interchange the position, then you have a minus sign in front of it. Now, do you see the bad guy? Yes, the bad guy is x minus 2. And because so we're looking at the limits, x approaching 2, so x does not equal 2. So that's why we can cancel it. Then we have x minus 5, -4 plus 2x plus x squared. We're ready. See, we're ready. We can plug in the number again. So 2 minus 5 minus 4 plus 2 times 2, 4. 2 squared is also 4. Wow. 2 minus 5 is negative 3. Negative 12. Oh, the answer is 1 over 4. So far, so good, everybody? Okay, let's continue. Okay. So let's look at this problem. So when we try to plug in h is 0, well, the numerator, you get 1/2 minus 1/2. Oh, that's 0. The denominator, we also get 0. So, you see, 0 over 0, it means there is a bad guy. So, in this case, how do we do it? Well, you can see this is actually not polynomial. It's actually like fractions. So that's why we have the third case. If you see fractions, you want to combine and into a single fraction, and we can simplify. Hopefully, you will see the bad guy. So how can we combine? Well, the common denominator is 2 plus h and 2. Okay, and the first factor, how do you get this guy? Well, you multiply the numerator and denominator by 2. The second term, 1/2, how do you get this? You multiply by the numerator and the denominator by 2 plus h. But don't forget your baby. Who's your baby? Parentheses. So don't forget the parentheses. If you miss the parentheses here, you'll be wrong. So be careful. Don't forget your baby in the mall. He or she will cry. So lonely. Okay. So next, we continue, right? So 2 plus h, 2, and then we have h. Well, here, the distribute minus 2 minus h. Alright. Can you see something we can cancel? Well, that is what we can cancel. And then, here. Remember a over b over c over d? If you see fraction in fraction, what do you do? So that's the same as multiply by the reciprocal, d over c. So, negative h is on top or bottom? On top. 2 plus h, top or bottom? Bottom. 2, top or bottom? Bottom. How about this h? Well, this h is like the c, right? You can think about it as like h over 1. So c is h. Well, c, where do you put the c? Bottom. Now, can you see the bad guy? Well, the bad guy is h. It makes the numerator and denominator 0 when h goes to 0. So we cancel it. We are like the police, right? So, we cancel it. Now we're safe. We can plug in h is 0. Oh, so you see, we get our limits. Minus 1/4. So far, so good, everybody? Okay, so when you watch the videos, you can control the speed, the pace. You can also pause and think more. I strongly recommend you to pause the video and then try the problem first. And then after you're done, you can check your answers with me. Okay, so let's continue. Well, look at this problem. When we plug in 2, what happened? 2 plus 7, 9. Square root of 9 is 3. 3 minus 3, 0. 2 plus 2, 4. Square root of 4, 2. 2 minus 2, 0. Okay, so I hope that when you calculate your, when you do your homework or exams, try not to use your calculator. By the way, for our quiz, we're not allowed to use calculator anyway. So I strongly recommend you for your homework, don't use calculator. Okay? So in the exams, you use your calculator to check your work. Okay? After you're done, use your calculator to check your work. But don't when you're doing your, when you're solving the problems, don't use calculator. Okay? You really want to get familiar with the numbers, build up the sense with the numbers. Okay? Alright, so we know 0 over 0, it means there is a bad guy. Okay, so which case do we have? Oh, we have difference of square roots. For difference of square roots, what do? We multiply by the conjugate. So actually here we have both the numerator and the denominator. We have the difference of square roots. So we actually need to multiply the conjugate of both of them. Okay, so now what happened? I'm gonna use my color to show you. Okay, numerator, group this together, multiply them out. Okay, so what do we get? Well, remember a minus b times a plus b is a squared. A squared is x plus 7. Square roots and square cancel. Minus b squared, 3 squared is 9. So this is what we get actually. Okay, and then we still have the term square root x plus 2 plus 2. Okay, how about the denominator? Well, denominator, I want to multiply this guy and this guy together, right? Then I have a minus b, a plus b, that's a squared, which is x plus 2, square root square cancel. Minus 2 squared, which is 4. Okay, and what's left? We have x plus 7 and 3 left. So far, so good. And let's continue. X plus 7 minus 9, we get x minus 2. And then we have x plus 2 and 2. Here, 2 minus 4 is negative 2. So, do you see the bad guy now? Yes, the bad guy is x minus 2. When x goes to 2, it makes the numerator and denominator 0. So let's cancel the bad guy. We have square roots x plus 2 and the 2, x plus 7 and the 3. Now we're safe. We can plug in the number again. So 2 square root of 4, 2 plus 2. 2 plus 7, 9, square root of 9, 3. Oh, so we have 4 over 6, which is 2 over 3. Okay, so this is our answer. So follow the steps, and then we can get it. Okay? Example 6, let's continue. Alright, so here, let's plug in 4. 4 times 4, 16 minus 7, 9. Square root of 9, 3. 3 minus 3, 0. And the denominator, well, the denominator, okay, so 4 square is 16. 3 times 16, 48. 48 minus 4 times 11 is 44. So 48 minus 44 minus 4 is actually 0. So we actually get 0 over 0. Okay, and then for the numerator, you see, is a difference of square roots. So what do we do when we see difference of square roots? So I strongly recommend you to try this problem. So pause here and try this problem first, okay? And then you can continue, watch the video, and check your answer. In this way, you can think and you learn from it. How about the denominator? Denominator is a polynomial. We can factor it. Alright, so how can we factor it? 3x and x. How do we get negative 11? Well, negative 4 will give us negative 12 plus 1. So negative 12 plus 1 is negative 11. Alright, let's continue. Well, the numerator, a minus b times a plus b is a squared, which is 4x minus 7, minus b squared, which is 9. And then the bottom, we just copy everything here. Okay, now, what happened to the numerator? Negative 7, negative 9 is negative 16. Can you factor something? Yes, we can factor out the 4. Then we have 4x minus 4. Wow, what happened? Can you see the bad guy? Yes, the bad guy is x minus 4, right? So after we cancel the bad guy, we have limits x goes to 4, and then 3x plus 1, square root of 4x minus 7 plus 3. Alright, so now we can plug in the 4. So we have 4. 4 times 3 is 12, so 13. And then 4 times 4, 16 minus 7, 9. Square root of 9, 3. 3 plus 3, 6. Oh, we can cancel it. So the answer is 2 over 39. Oh, actually, by the way, here, because I already plug in the x values, so if there's no x, then you don't need the limits. You need the limits if there is x in your expression. Okay, but if you only get numbers, then you don't need the limits. So far, so good, everybody? Alright, let's continue. Okay, so next we're gonna talk about the squeeze theorem. So what is the squeeze theorem? Well, squeeze theorem is also called the sandwich theorem. Okay, so we have three functions, f, g, and h. So f is the smallest function, and h is the largest function, and g is in the middle. Okay, so g is bounded between f and h. So if we know the relation, okay, g is bounded by f and h when x is near a, except possibly at a, and if f and h have the same limit L, so this is the limit L, then if forced, the middle guy must have the same limit. Okay, so you can see this picture, it's like squeeze the g has to have the same limit. Okay, so that is the squeeze theorem. So we have like two conditions here. So one condition you want to check is you want to find the two boundary functions f and h, right? And then the second condition is you want to show those f and h, they must have the same limits at a. Okay, so after you check those two conditions, then you can use the squeeze theorem, and our conclusion is the middle guy must have the same limits. Okay, so let's look at this problem. Okay, so how do we find the boundary functions? Well, x cubed is not bounded, right? But sine is bounded. So you start with the sine. I don't care what the angle is, but the sine is always bounded between 1 and minus 1. Okay? So this is the first step. And then how do you change from here to there? Well, you think about, well, it looks like we multiply by 7x cubed. So let's multiply by 7x cubed for each of the term. So minus 1 times 7x cubed is minus 7x cubed. And this is 7x cubed sine 2 over 5x and 7x cubed. Is that right? Well, you're gonna be careful, because if you add or subtract any number, the inequality sign won't change. If you multiply or divide by a positive number, the inequality won't change. However, if you multiply or divide by a negative number, the inequality will flip. Right? So here, x cubed could be positive and it could be negative. So when x cubed is positive, well, this is true. But when x cubed is negative, you're gonna flip the sign. So there is, so you either separate into two cases and say if x is positive and then you do the inequality, or if x is negative and you do the inequality with the inequality flipped. Okay? There's one way to avoid separate into cases is by, okay, look at me carefully, is by put an absolute value here. Then this is true no matter x is positive or negative. Okay, because 7 absolute value of x cubed is always positive, and the negative 7 absolute value of x cubed is always negative, then this guy is always bounded between both of them. Okay? Bounded between them. So that's why this is a useful trick. So don't put the absolute value here, because if you put the absolute value here, this is not the function we're looking for. We want the middle guy is exactly what we're looking for. Okay, so you put the absolute value in the boundary for the in the boundary functions. Okay. So this is the first condition. We find the boundary function, and then next, let's check the limits for each boundary function. And x goes to 0. Okay, so when x goes to 0, absolute value of x goes to 0, right? We can just plug in 0. Then this is 0. And this guy limits x goes to 0, 7, and absolute value of x cube is also 0. Then we can say by squeeze theorem, our middle guy also have the same limits, 0. Okay, so this is the complete proof of our problem. Okay, so you need to mention squeeze theorem because this theorem has a name. Okay, so if you forgot to mention the squeeze theorem, you will lose 1 point in the exam. Okay, so don't forget that. And we mark here. Okay, so we mark a squeeze theorem is very useful when you see like polynomial times sine function or polynomial. It's not necessarily polynomial, it could be any power function. Okay, times cosine, because sine and cosine, they're always bounded between -1 and 1, and then you multiply by the power function of polynomial, then it's very similar steps. And maybe one more, it could be polynomial or power function, right, times arctangent, right? You know arctangent is also bounded between not -1 to 1, but minus pi over 2 to pi over 2. So it's also bounded between two numbers. So so they're useful. Okay, so think about squeeze theorem in that case. And that is session 2.3. All right, so have a good day. Bye.